Okay, let's talk about something really interesting. In pretty much every complex network, there's this silent guardian working 24/7 to prevent a total meltdown. It's called the spanning tree protocol. And while it's designed to be your network's biggest hero, one wrong move can turn it into the villain that brings the whole thing crashing down.
And that right there is the big paradox we're going to unpack. How can something so vital for keeping things stable also be so fragile? This protocol basically walks a razor's edge between perfect order and absolute chaos. Understanding how it works is absolutely key to building a network that won't let you down.
So, to get why Spanning Tree Protocol, or STP as we'll call it, even exists, we first need to talk about a true network nightmare. And the scary part is it's caused by something that's supposed to be a really good thing: redundancy.
Now, this is where a really smart design can just completely backfire. You build extra links between your switches, right? So if one cable gets cut, traffic just zips along another route. It's brilliant for keeping things online. But those extra paths, these loops, they create a hidden ticking time bomb. Without a traffic cop telling packets where to go, the network just descends into chaos. You'd be shocked. It's not some massive attack or a huge hardware failure. It's a single, tiny data frame. Just one broadcast message, think of a device just asking a simple question, gets sent out, and if you've got loops, that one message gets trapped in a deadly, never-ending cycle. And here's where it all spirals out of control. A switch gets that broadcast, and it does its job. It floods it out every other port. But in a loop, that same frame comes right back to it, and it gets flooded again, and it just multiplies exponentially. We're talking seconds here. This broadcast storm eats up 100% of your bandwidth, the network is totally choked, no real data can get through, and, well, it's lights out. Total shutdown.
And this is where our silent guardian, STP, finally steps in. It's that traffic cop we were talking about. It takes a look at all the physical roads in your network and draws a single loop-free map, kind of like a tree with all its branches. Now, it doesn't get rid of those extra redundant links. It just puts them in a standby or blocked state, ready to be activated in a heartbeat if the main path ever fails. Okay, so how does it build this logical tree map? Well, the very first thing STP does is it forces all the switches to hold an election. They have to pick a single leader, which we call the root bridge. This one switch becomes the center of the network universe, the main reference point for every other decision about which path to take. The election itself is super simple and totally automatic. First, all the switches look at their bridge priority number. By default, they're all set to the exact same value, so it almost always comes down to the tiebreaker. The switch with the lowest MAC address wins the election. It sounds fair, right? But this is where things can go so wrong. And this quote from Kevin Dooley just nails the problem perfectly. If you leave this critical decision up to chance, Murphy's Law kicks in. Your oldest, creakiest, most underpowered switch could suddenly become the core of your entire network just because it happened to have a low MAC address. All your traffic then tries to squeeze through this tiny bottleneck, and your network becomes slow and incredibly unstable. So, the takeaway here is absolutely crucial. You have to take control of this election. Don't let your network randomly pick its leader. You need to go in and manually set the bridge priority on your biggest, baddest core switch to a really low number, like 4096, to guarantee it wins every time. And for good measure, configure your backup core switch with the next lowest value, 8192. That way, you get a stable, predictable, and fast network. Now, even if you've done everything right and picked a great root bridge, the original spanning tree protocol had this one massive flaw that just doesn't fly in the modern world. It was unbelievably slow to react when things changed. Think about it, a 30 to 50 second network outage every single time a link fails, or even when someone just plugs in their computer. I mean, that's just completely unacceptable today. That's long enough for your VoIP calls to drop, for critical applications to time out, and for your help desk phones to start ringing off the hook. This incredible slowness is exactly why STP had to evolve. And its successor, Rapid Spanning Tree Protocol, or RSTP, fixes this problem directly. As you can see here, the difference is just night and day. We go from a convergence time of almost a minute down to less than 10 seconds. And honestly, it's usually just a couple of seconds in the real world. It pulls this off by using smarter port roles, like alternate and backup, which basically keep those standby paths warmed up and ready to take over instantly. The good news here is that pretty much any modern switch you buy today is going to default to a rapid version like RSTP.
So the big takeaway is simple. Pick one of these modern protocols and just make sure you're running it consistently on every single switch in your network. If you start mixing and matching, you're just asking for trouble and slow recovery times. Okay, so we've picked a strong leader, we're using a fast protocol. We should be golden, right? Well, not quite. Because STP was designed in a more trusting time, it can be exploited, either completely by accident or by someone with bad intentions. The classic attack is called a root bridge hijack. An attacker just plugs their laptop into an open network port and starts blasting out fake STP messages. We call them BPDUs, with a priority of 0. That's even lower than your carefully configured core switch. The network, not knowing any better, trusts these messages, holds a new election, and bam, the attacker's laptop is now the root bridge. They can now see or even disrupt all of your network traffic. The defense against this is a feature called Root Guard. You turn this on for any port where you should never see a new leader trying to take over, so ports that connect down to other switches you might not control. If some device on that port tries to claim it's the new boss, Root Guard just ignores it, protecting the real king of your network. A way more common issue, and usually it's just an accident, is when a user brings a cheap little switch from home and plugs it into their wall jack to get more ports. That little switch starts sending out its own STP messages, and it can totally confuse the network, cause random ports to shut down, and just create a lot of instability. For this scenario, we have BPDU Guard. Honestly, this is a must-have feature on any port that connects directly to a user's computer or phone. These ports should never, ever receive an STP message. If one ever does, BPDU Guard doesn't ask questions. It instantly shuts the port down, neutralizing the threat before it can harm the rest of the network.
All right, we've gone through the problem, the solution, how it's evolved, and the threats. Let's wrap this all up into a simple, easy-to-follow defense plan.
Okay, this is it. This is your checklist for a bulletproof spanning tree setup. First, the foundation. Use a modern, fast protocol like RSTP. No excuses. Second, take command of your network's hierarchy. Manually set your core switch to be the root and set up a backup. Then, you've got to harden your defenses. Enable Root Guard on ports pointing to switches outside your control, and enable BPDU Guard on all your user-facing ports. And here's a final pro tip. You can enable a feature called Port Fast on those user ports so they connect faster, but always, always use it with BPDU Guard.
So I think the big thing to take away from all this is that spanning tree protocol isn't a set it and forget it kind of thing. It's an active defense system, and it needs you to deliberately configure it to be a guardian. If you don't, it can easily become the very cause of the disaster it was built to prevent. So the real question you got to ask yourself is, on your network, which one is it?